In Chapter 5, we're going to start looking at factoring. Well, what is factoring? It may be something that you've heard of before, but maybe didn't quite understand what it was. Well, the main idea behind factoring is to kind of look for what we have in common. It's kind of the reverse of the distributive property. For instance, if we had a 3 out in front of an x minus 2, and you were told to simplify, you would automatically start distributing. You'd multiply out the 3 to everything on the inside, and that would get you a 3x minus 6. Distributing has us multiplying out that 3, but what factoring would do would take this 3x minus 6 and work in reverse and say, what do the 3x and the 6 have in common? Well, the 3x and the 6 both have a common factor of 3. They're both divisible by 3. So it would have you take out a factor of 3 from both, put it out in front, and put what was left over after you pull out the 3 from each piece, and it would leave you with putting those inside of a set of parentheses. I always think of the parentheses as kind of a place where you're putting your leftovers, kind of in a fridge to save for later. And what's really nice is when we're going in this direction to factor, is if you ever want to double check, you can just multiply out whatever you have or distribute out what you have. And that's a good way of double checking. So let's take a look at doing something like this. What it's called is factoring out what's called a greatest common factor. And a lot of times we'll kind of shorthand that into what's called the GCF. And what it means is we're going to look at all of our pieces and find out what they have in common and pull it out. When we say pull it out, we don't mean pull it out as in it will disappear. We mean pull it out in front of our piece, and then whatever leftovers we have will stay inside of a set of parentheses that are kind of acting like a little holding pen. So if we take a look at this first example, we've got 7x minus 14. So we look at our two pieces here, the 7x and the 14. What do they both have in common? Well, they're both divisible by 7, so we can pull out a 7 that's going to go out in front, so we pull it out in front, and then whatever's left over is going to be inside of a set of parentheses, a little holding pen to hold our leftovers. So if I pull out the 7 from the 7x, I will still have an x left, minus if I pull out or factor out or divide out of 7 from the 14, I'll still have a 2. And like I said before, if we want to double check this, I can multiply out the 7. If I multiply out the 7 to the x, I'll get 7x. Then the 7 times 2 does give me my original 7x minus 14. So that's my final answer, and I do need to rewrite this with the parentheses. I can't forget them. Those are absolutely necessary. Here's another one. On this next one, we've got 54m minus 45. So if I look at the 54m and the 45, what do they have in common? Well, they're both divisible by 9. So I can pull out a factor of 9 from both pieces. And then our leftovers here will go inside of the little parentheses that will hold our leftovers. So first things first, the 54m, I have to divide out or pull out the 9 first. Well, 9 goes into 54 6 times, and I'll still have my m, minus, now I have to also pull the 9 out of the 45. Well, that will leave me with just a regular 5, and then that's my final answer, is I've got a 9 that I pulled out of both the 54m and the 45, leaving me with a 6m minus 5. And that's my final answer. Let's take a look at this next one and see. We've got a 32x plus a 24. What do they both have in common? Well, 32 and 24 are both divisible by 8. So I can factor out in front an 8 or pull out an 8 to go out in front. Then our leftovers again will go inside of their own set of parentheses. Well, let's take a look. Dividing the 8 out of the 32 will leave us with a 4x. And dividing out the 8 from the 24 will give us a 3. And remember, there was a plus in the middle. And so we are done. And we always want to make sure that we're getting what's called a greatest common factor, not just a common factor. How I know I got the greatest common factor is if I look at the leftovers, the 4x and the 3, is they don't have anything in common. Had you just pulled out, let's say, a 4 instead of an 8, what you would have noticed is that these two numbers would still be divisible by 2, meaning you didn't get the greatest common factor. Yes, you got a common factor, but not the greatest, and you'd say, okay, let me back up. What could I have pulled out that was even bigger than 4? And you would have said, oh yeah, I can divide out an 8. So our final answer is 8 times 4x plus 3. Let's take a look at D. In D, we look at the 5z and the 5 and ask what do they have in common. Well, they're both divisible by 5. They both have a 5 in them. So I can actually pull out the 5 from each piece. The question is, if I divide a 5 out of each piece, what will be left? Inside of my parentheses as my leftovers. Well, if I had a 5z, pulling out the 5 just leaves you with the z plus. If I divide a 5 from my 5 on that last piece, I still have a hidden 1. And kind of the thought is 5 will go into 5 one time. And that's why you have that extra 1 there. Which makes sense. If you wanted to double check, you could distribute and you'd get 5z plus 5. If you had 2 pieces, you still should have 2 pieces. Now let's look at this last one in E. In E, we've got 8x minus 9. Now notice, 8x and 9, they don't have anything in common. They're not both divisible by something. So there's actually nothing you can factor out. And we use a special word when there's nothing you can factor out. We call it prime. That's our way of saying that it cannot be factored. Everything else, we were able to pull something out. Whether even it's just a number 5 or number 2, you're able to pull something out. But if you can't pull out anything, we're going to call it prime. Let's